On August 9, 2018, a recovery team marks out a search area over the surface of Lake Kulonga in the Murmansk region. The operation is run by the Winged Victory Memory Foundation. Their target is a specific factory number attached to a single documented loss in Northern Fleet Air Force records. They are searching for a single-seat variant of the Ilyushin Il-2 that vanished on August 22, 1943. The historical record states the aircraft was damaged by anti-aircraft fire during a combat run against Luostari airfield. The dossier indicates the pilot, II Kalichev, performed a forced landing on the water and survived. He escaped the sinking machine and returned to friendly lines. This is the documented history. However, when the dive team reaches the bottom, the physical evidence presents an immediate contradiction. The aircraft is resting at a depth of about 10 to 11 meters, roughly 33 to 36 feet. The water in Lake Kulonga is fresh, which often aids in preservation, and the visibility allows for a clear visual inspection. The divers confirm the presence of the forward armored tub and the metal wing structures. The aircraft sits upright in the silt. But as the survey cameras move toward the cockpit, they reveal a closed canopy. The sliding hood is pulled shut against the windscreen. In the discipline of underwater aviation archaeology, a sealed cockpit is an immediate pause point. It can suggest the pilot never got out, but it can also be a mechanical illusion created as the airframe sinks, shifts, and settles. Either interpretation carries consequences. If the pilot died inside, this site is a war grave. Legal and ethical protocols would strictly limit any disturbance of the wreckage. The recovery plan depends entirely on resolving this discrepancy. The team must determine if the paperwork is wrong or if the wreckage is misleading. A survivor account written in 1943 may be inaccurate, or the aircraft on the bottom might be a different machine entirely. The divers approach the glass to verify the contents of the cockpit. The inspection reveals that the cockpit is empty. There are no human remains inside the armored shell. The pilot seat is vacant. The mystery is resolved by mechanics, not by rewriting the archive. It is highly probable that the hood was left open during the pilot's escape, but slid shut during the descent. The impact with the lake bed or the angle of the glide underwater forced the mechanism back into the locked position. The canopy sealed itself after the pilot was gone. This visual confirmation aligns the physical evidence with the survival record of pilot Kalichev. The site is classified as a recovery zone rather than a grave. With the ethical constraint removed, the engineering challenge begins. The aircraft has sat in the sediment for 75 years. The objective is to retrieve the airframe for transport to Novosibirsk, where the foundation plans a full restoration with the stated aim of returning it to flight condition. This goal imposes strict limits on how the wreck can be handled. A standard salvage operation might prioritize clearing the waterway, using heavy chains or cutting torches to break the object into manageable pieces. A forensic recovery for restoration requires the opposite approach. The team must treat the aircraft as a single, fragile artifact. They cannot attach cables to weak points. They cannot risk snapping the spars. The shallow water helps the team in one specific way. The shallow depth allows divers to work for extended periods without complex decompression schedules. They can survey every inch of the airframe to determine structural integrity. They find that the forward section, the engine, and the armored tub are solid. The metal wings appear securely attached to the center section. However, as the inspection continues toward the tail, the survey team identifies a critical gap. The airframe loses continuity here. The transition from the armored steel center to the tail section reveals a massive structural discontinuity. The rear of the aircraft is effectively missing. This is not impact damage. It is a specific consequence of the materials used in 1943 interacting with the lake water for 7 decades. The recovery engineers must now formulate a lift plan for a machine that has lost half of its structural spine. Here, freshwater chemistry and silt burial shape what the lake has preserved. In saltwater, decades of immersion often reduce an aluminum airframe to a weakened lattice of corrosion products, especially where dissimilar metals meet. Lake Kulonga offers a different chemical profile. The freshwater is typically less conductive than the ocean, which can slow galvanic attack, and the silt can limit oxygen access to some surfaces, improving preservation in places. However, the preservation is not uniform. The Ilyushin Il-2 was manufactured using a mixed construction technique to save strategic metals during the war. The forward section, housing the engine and the cockpit, is a rigid armored shell made of steel. The wings and control surfaces are primarily metal, but the rear fuselage of this specific variant was built as a wooden monocoque structure. This hybrid design creates a split timeline for degradation. While the metal components stabilize in the cold freshwater, the organic components are subjected to biological and chemical decay. Over 7 decades, the waterlogged wood loses cohesion as bonds fail and fibers separate, even as the metal settles into cold water stability. The steel armor tub remains nearly as strong as the day it was built. The aluminum wings retain their shape and surface detail, but the wooden spine that connects the tail to the cockpit has disintegrated entirely. The survey team finds the metal tail stabilizers and the rudder lying in the silt, physically disconnected from the main body of the aircraft. The structure has not been destroyed by impact forces, it has been dismantled by the environment. This condition forces a specific reconstruction of the lost mechanics. The damage pattern suggests that the aircraft did not break apart upon hitting the water. If the fuselage had snapped on impact, the debris field would be more likely to show signs of twisting, tearing, or high-energy scattering. Instead, the heavy components are sitting upright and aligned. This is consistent with the conclusion that Captain Kalichev executed a controlled ditching. He brought the aircraft down at a low angle and a survivable speed, bleeding off kinetic energy across the surface of the lake before the machine settled. The loss of the fuselage occurred long after the event, a slow-motion collapse caused by the material limitations of the wood rather than the violence of the crash. That verification immediately hardens into an operational constraint. The team cannot simply wrap slings around the nose and tail to hoist the aircraft as a single unit. The structural continuity of the airframe is broken. There is no longer a rigid keel to distribute the load. The armored tub and the wings effectively form a single, nose-heavy mass, while the tail section exists as a separate collection of parts. The engineers must treat the recovery as a component-based operation. The primary objective becomes the extraction of the center section. This is the heaviest and most valuable part of the find. It contains the engine, the cockpit instruments, and the armored protection that defines the Sturmovik. But without the balancing weight of the tail, the center of gravity shifts dramatically forward. Any attempt to lift this section requires a precise understanding of its new geometry. The team must apply lifting force directly to the surviving hardpoints on the center section without inducing torque that could snap the wing roots. The environment has preserved the metal, but it has removed the leverage required to move it easily. The static stability of the wreck on the lake bed is deceptive. Once it leaves the support of the silt, the physics of the lift will change instantly. A submerged aircraft is an anonymous collection of industrial components until a specific piece of evidence connects it to a name. In the Murmansk region alone, hundreds of aircraft were lost during the war. Finding an Ilyushin Il-2 on the bottom of Lake Kulonga is significant, but without positive identification, the historical value of the airframe is capped. It remains a generic example of the type rather than a witness to a specific moment in history. Before the engineering team can authorize the physical stress of a lift, they must satisfy the requirements of forensic context. This concept defines the sequence of the operation. Forensic context is the principle that an artifact loses a portion of its data the moment it is moved from its resting place. The relative position of debris, the setting of the cockpit controls, and the condition of the paint are all fragile indicators. If the team rushes to hoist the wreck, they risk destroying the evidence that proves its identity. The investigation must be completed on the lake bed. The divers are not just salvage operators, they are the first historians to view the site. They must locate a serial number, a unit marking, or a distinctive feature that correlates with the archival loss registers. The disintegration of the wooden fuselage described in the previous chapter actually assists this process. While the collapse of the structure creates a lifting problem, it separates the tail surfaces from the main body, making them accessible for close inspection. The survey team locates the vertical stabilizer and the rudder lying in the silt. These components are often the first to be lost in a high-speed impact, but here they are intact. The divers clean the sediment from the control surfaces and document something that has survived 75 years of immersion. On the metal rudder frame, sections of the original fabric covering are reported to remain in place. On that fabric, surviving paint still shows a distinct red star. This marking provides the initial confirmation of the aircraft's allegiance and era, but the investigation requires more precision to name the pilot. The team cross-references the location of the wreck with the combat reports from the Northern Fleet Air Force. The recorded crash location is consistent with the loss report filed for August 22, 1943, within the expected uncertainty of wartime coordinates. The proximity to the attack corridor for Luostari airfield matches the flight path of a specific flight. The archives identify the pilot of this machine as Captain II Kalichev. The records provide the biographical data necessary to close the loop on the survival question. Kalichev was born in 1909. The military ledger confirms that he not only survived the ditching in Lake Kulonga, but continued his service. He transferred from the Black Sea Fleet to the Northern Fleet, fought through the remainder of the war, and did not retire until 1955. He left the service with the rank of lieutenant colonel. This biographical lock changes the legal status of the recovery. The empty cockpit now makes sense. No human remains are observed in the cockpit or the immediate survey area around the wreck. With the survivor record in hand, the legal question is settled. This is a recoverable historic crash site. This verification provides the green light for the Winged Victory Memory Foundation to proceed with the removal. The paperwork and the wreck now match. What remains is how to raise it intact. With the identity secured, the only adversary left is physics. The Il-2 is a heavy aircraft by design. The forward section is a structural shell of steel armor plate intended to deflect ground fire. In 1943, this weight was counteracted by the lift of the wings and the thrust of the engine. On the lake bed, it is dead weight sunk into the silt. The recovery team faces a specific mechanical problem: how to neutralize the weight of the armored tub without applying crushing force to the corroded aluminum wing roots. The solution relies on the principle of lift bag buoyancy. This is the designated engineering concept for the vertical transport phase. A lift bag is not simply a balloon attached to a wreck. It is a tool for controlled displacement. The mechanics are precise. To generate lift, the divers attach deflated pneumatic bladders to verified hardpoints on the center section and the wings. They do not use chains or steel cables, which concentrate stress on single points. The bags distribute the lifting force across a broader surface area. When the team introduces compressed air into the bags, the air displaces the water inside. Since air is significantly less dense than water, this creates a net upward force. The critical variable in this process is control. If the bags are overinflated, the aircraft will tear itself free from the suction of the mud and rock it to the surface. An uncontrolled ascent expands the air in the bags rapidly as the water pressure decreases, increasing the speed of the rise and risking a collision with the surface support vessels or a catastrophic structural failure of the airframe. The team must modulate the air supply to achieve neutral buoyancy first. They gently break the seal of the silt, allowing the aircraft to hover just above the bottom. Only then do they add the final volume of air required to bring the machine to the surface in a controlled, slow-motion ascent. Before the main lift, the divers remove the loose tail pieces, the tailplane, the Red Star rudder, and the tail wheel, so nothing can snag or drift during the heavy ascent. The heavy lift focuses strictly on the center section and the wings. The divers rig the bags to ensure the aircraft remains level. Because the wooden tail is missing, the center of gravity is far forward. The rigging geometry must account for this imbalance to prevent the aircraft from pitching nose down and driving the engine back into the mud. When the lift begins, everything follows the hydrostatic plan. The compressed air lines hiss, the bags inflate, and the armored shell lifts free of the sediment. For the first time in 75 years, the Il-2 is suspended in the water column. It breaks the surface gently, supported by the pontoons. The aircraft is now floating again, but it is an unstable vessel. It has high drag and no propulsion. The recovery vessels secure lines to the floating assembly. The next phase is the tow. The team must move the suspended airframe from the deep water of the crash site toward the recovery point on the shore. This is a delicate transit. The water acts as a cushion, supporting the structure, but the drag forces on the wings create stress. The towing speed must be kept to a minimum to avoid shearing the wings off the center section. The convoy moves slowly across Lake Kulonga, the same body of water some English-language accounts call Lake Krivoya, bringing the prize closer to land. The depth problem is solved, but the shoreline imposes a new geometry. A shallow, boulder-strewn shelf keeps a crane barge at standoff distance. Its draft too deep to approach, its boom too short to reach. The aircraft floats just offshore, close enough to see and far enough to be untouchable. The team has conquered the lake bed. Now they are blocked by access. How the operation runs into an access problem, pure geometry. In heavy salvage, the machinery is usually positioned to lift the load vertically and place it directly onto a transport deck. Here, the geometry denies that vertical solution. The angle of approach is horizontal. The aircraft must be brought out of the water along the surface of the terrain. The friction and the impact potential of the granite boulders create a corrosion trap for the thin aluminum skin of the wings. If the team attempts to drag the aircraft directly over the rocks, the friction will shred the underside of the wings and the radiator housing. The armored tub might survive, but the rest of the airframe would be sacrificed. The engineering solution is to construct a sacrificial interface. The team cannot remove the rocks, so they build a surface to glide over them. They construct a heavy timber skid on the shoreline. This is not a factory tool, it is a site-specific adaptation. The skid is a sled made of wooden beams designed to cradle the fuselage and distribute the weight. They line the timber frame with used rubber tires. The tires serve two distinct mechanical functions. First, they provide a cushion that conforms to the irregularities of the aircraft's underside, preventing point loading on the rivets and seams. Second, they act as a buffer against the rocks below if the skid flexes or bottoms out. With that improvised buffer in place, the pull can begin. The extraction sequence is a study in friction management. Lines are run from a shore-based winch to the floating airframe. The team guides the aircraft manually until it sits above the submerged portion of the skid. As the winch takes up tension, the lift bags are deflated and the weight of the Il-2 settles onto the tires. The physics of the situation changes instantly. The aircraft loses the uniform support of the water and becomes a heavy, dead load resting on the sled. The winch pulls the entire assembly up the gradient. The timber runners slide over the mud and rocks, taking the abrasion that would otherwise destroy the artifact. The aircraft moves inch by inch out of the lake. Water drains from the internal cavities of the wing roots and the armored shell. For the first time since August 1943, the Ilyushin Il-2 is fully supported by the ground. Once the aircraft is high and dry on the bank, the recovery mode switches to disassembly. The sled provides a stable work platform. The engineers can now access the wing attachment points. To transport the aircraft, the wings must be separated from the center section. The bolts, seized by decades of tension and corrosion, are carefully removed. The outer wing panels are detached, reducing the width of the load to fit standard road transport dimensions. The skid system has successfully bridged the gap that the crane could not cross. The aircraft is no longer a wreck in a lake. It is a collection of secured components ready for the road. The most dangerous physical variables have been neutralized. The final phase is logistical. 75 years separate the ditching from the recovery, a span in which the aircraft existed only as a submerged target. Now the operational clock resets. The recovery phase is complete, and the conservation phase begins. The aircraft is disassembled on the shore of Lake Kulonga. The wings are secured on flatbed trucks, separated from the armored center section. The convoy begins the long overland transport from the edge of the Arctic Circle to the industrial center of Novosibirsk. The destination is not a museum display floor. Their goal is to make it fly again. This goal introduces the concept of restoration viability. In the world of aviation archaeology, not every recovered airframe is a candidate for flight. Most saltwater recoveries are too corroded to bear aerodynamic loads. They are stabilized solely for static exhibition. A flight restoration requires a different standard of structural integrity. The engineers in Novosibirsk must determine if the core of the aircraft can ever be trusted to carry a pilot again. The Il-2 from Lake Kulonga presents a specific case study in this viability logic. Superficially, the aircraft looks incomplete. The entire rear fuselage is missing. However, in the engineering hierarchy of the Sturmovik, the wooden tail section is a rebuildable rear fuselage structure. The structural heart of the aircraft is the armored tub that protects the engine and the cockpit. This steel shell carries the wing spars, the engine mounts, and the landing gear loads. Because the freshwater environment appears to have preserved much of this steel core, a flight-worthy restoration becomes plausible. The DNA of the aircraft, its identity, and its primary load path is intact. The wooden fuselage will be manufactured from scratch using original plans, but the machine that flies will physically be the same machine that Captain Kalichev landed on the water. The conservation process begins with a complete teardown. Every rivet, bolt, and panel is removed. The mud of the lake is washed away to reveal the original factory paint and the battle damage from 1943. The internal systems, the gauges, and the control linkages are cataloged. The empty cockpit, which caused such concern during the initial dive survey, becomes a workspace for the restorers. They will reinstall the controls that Kalichev used, matching the configuration to the technical manual. Of the period, the legacy of this operation is measured in the continuity of the artifact. In 1943, the loss of the aircraft was the price paid for the survival of the pilot. Captain Kalichev abandoned the sinking machine to save his own life, a rational trade that allowed him to fly again and serve until 1955. For 7 decades, the pilot lived while the machine died. Today, the roles are reversed. The pilot is gone, but the machine has been resurrected. The recovery at Lake Kulonga demonstrates that even a partial wreck can support a total restoration if the critical components survive. By utilizing the tire-lined skid to overcome the shoreline barrier and applying strict evidence discipline to verify the history, the team successfully bridged the gap between the lake bed and the workshop. The aircraft is no longer a debris field on a sonar map. It is a tangible engineering asset, entering the slow, precise work required to turn a 75-year-old static object back into a flying machine. The extraction is finished, the rebuild begins,